Okay, in the last video, we introduced a new concept, which is gravitational field strength and how that relates with the Earth as well as the calculations that we'll be making. We also talked about acceleration due to gravity, and we said the acceleration of field force is actually a constant 9.81, and it's a constant because on the surface of the Earth, the field lines appear to be parallel, or it doesn't change so much because the change in height that we experience is negligible in comparison to the radius of the Earth. In this video, we're going to be continuing. Now, our point or what we're now focusing our energy on is sketching a graph that shows the variation of G against R. Okay, so we want to see how does the value of G change as we are moving from the center of the Earth up until a certain point, right? And questions will give you this graph, either asking you to sketch it accurately, which we're going to do together, or it's going to ask you to describe or obtain information from a given graph that you'll be seeing. So let's get to it. First of all, before we plot, we need to make a couple of assumptions, right? Physics is a lot of assumptions, guys. If you're not yet used to assumptions, you haven't yet started doing physics. But essentially, before we plot anything, we need to understand that the density of the Earth is uniform, right? So we're going to assume that the Earth has uniform density, the mass itself. So if you're looking at this being the Earth, the mass of the Earth, which is m, is essentially uniformly distributed, right? In reality, this is not true. For example, most of the mass of the Earth is concentrated at the core, but then elsewhere it's getting lighter and lighter and lighter. But for argument's sake, we assume that the density is uniform. Okay. We also assume that the surface of the Earth is uniform, so it's flat, and the Earth is a uniform sphere. So we're assuming there are no mountains, there are no valleys, there is none of that. Right? So those are two assumptions that we're going to be making when we're trying to plot the graph of G against R. So essentially, the graph will look as follows, right? And I'm going to explain why this graph is exactly the way it is. So first of all, we're going to start in the surface of the Earth. Okay, so in the center of the Earth, which is like this, we're going to assume that the value of G itself is directly proportional to R. Okay, so this holds water, or this is true when we start from the center and we want to move outwards to that specific point. So this is the region where G is directly proportional to R, and it actually makes sense for us to be actually saying that. So from that point to that point, we can therefore say G is directly proportional to R. Why is this true? Why is G directly proportional to R when we start from the center and we move towards the surface of the Earth? Well, it's a assumption that we can make, so I'm not going to go through it because it's not in the syllabus, but I'm just gonna explain it a little bit, right? So we know that density is equal to mass divided by volume, okay? And we say that the Earth is of uniform density, so the mass will be equal to density multiplied by volume, okay? But you know that the volume of so my mass is here. The volume of the Earth, since we've assumed that it's a sphere, will be 4 over 3 pi r cubed. Okay? And then the mass of the Earth, remember we had gm over r squared is equals to g. So g r squared, right? So we want to find m, will be g r squared over g is going to be equal to the density 4 over 3, okay, pi r cubed, right? So r squared and r cubed, that cancels out. So you're now left with g is equal to rho, that big G, 4 over 3 pi. All of that is a constant multiplied by r. So now you can easily see that, hey, G and R are actually variables that are changing. The rest, all of this, is a constant. So, hey, G is directly proportional to R. So if you're from the center of the Earth moving towards the surface, G is going to be directly proportional to R. And it's going to be 9.81 close to the surface over here. So it's going to be 9.81 at that specific point. So you're going to see a straight line indicating direct proportionality, which we have seen over there. But as you escape the planet, it becomes different now. There isn't any mass of the Earth to talk about. So we can't have the same rule that was applying when we're inside the Earth and still have it applying when we're outside of the Earth. Things become a little bit weird, right? So the moment we get outside of the Earth, and we're now talking about these distances, right? No matter how big it's going to get, the rule that now applies is G is equal to gm over r squared only. right? So we now can't talk about how the mass is going to influence anything because there's no mass of the earth to begin with. So we can't talk about a formula that involves density. We can't do that anymore. We can now just use this formula alone. So from this formula, you can now see that G is now directly proportional to 1 over r squared. Okay? So you see that the rule has changed when you're now outside of the earth, and it's different from when we're inside the earth. So you can now see that the graph will look like this little curve over here, right? Why is this a little curve? If you go in Desmos and you punch the graph of y is equals to 1 over x squared, you're going to see those two little graphs. So that's how a graph of that relationship looks like. So that's how I knew that was going to be a curve like that. So you can now see that outside of the earth, so this is the earth's surface over here, right? Let's just say S for surface. So outside of the earth, the graph is going to look like that. From the center of the earth towards the surface, the graph is going to be a straight line. So that's why you need to be very careful of that. Some questions can ask you to accurately plot this graph. So sketch it accurately. As you're seeing on the graph, I've shown you a question that asks you to do that. So you need to know how to do that. So essentially, accurately sketching is just knowing what is the value of G at this point, at this point, at this point, and then just trying to draw a rough sketch as you possibly can. Okay, so the specific points that you must know how to plot. The first one is the center, which we've already talked about, which is at 0. Okay, so the center here is at 0, which is over here. And you now know that at that point, at the surface where we have r, the radius r, the value of G is actually going to be equal to 9.81. Okay, so those 2 points are very easy for you to plot because you're just looking at, hey, okay, I have that point, let me draw a straight line. But outside of that, you don't know where these points actually come from. So I have these 2 points that I need you to be mindful of. 1 point at 2r, twice the distance r. How did I get 0.25 G? We're going to talk about that. At 3r, how did I get 0.11 G? We're also going to talk about that. Okay, so let's start. If you're at a specific distance r from the center of the earth, so if you're here at the surface of the earth, G will be equal to gm over r squared. So for argument's sake, I'm going to assume that gm is equals to k. So gm over here is equal to k. So that's why I have a constant k, which has replaced the value of gm to make the calculation simpler. Okay, so if you want to move r to become 2r, right? So you want to move twice the distance. And you want to find out what is the new value of G in terms of the old value of G. What you're going to do is you're going to say G1 will now be equal to K. The value of R now is going to be equal to 2r squared. Okay, so that's the difference. So it's now 4r squared. Okay, so we have 4r squared over here. Okay, and we now know that the value of K is actually equal to GR squared. Okay, so from that assumption that we've just made, I can now replace the value of k at the top. So this value of k, put gr squared. Below we have 4r squared. The r squareds cancel out. I'm left with g over 4. So I can see that if I move a distance of 2r, twice the value of the radius, I'm going to have a value of g, acceleration due to gravity, of g over 4, 0.25. So if I go on the graph here, I can now say at 2r, the value that I'm plotting is going to be 0.25. So if you're asked to plot this graph, you have to graduate the axis. You usually be given 3 marks. You have to graduate the y-axis and actually say, hey, I'm at 0.25 G. Okay. So at the value of 3r, the same logic, k over 3r squared. That's 9r squared. The value of k is g over r squared. R squared and r squared cancel out. So we're left with g over 9, which is 0.11111 G. Okay. So now you can see that, hey, 0.11 G aligns with 3r, which is over here. So essentially, that's how you're going to plot this graph. So you can have even 4r, you can even have 5r, you can plot these different points, and they're just going to get progressively smaller as you will be approaching bigger and bigger distances. So that's how you can plot the graph. That's the variation of G against R, both within the surface as well as you get outside of the surface. And yeah, different questions will ask you. For example, this question, they can ask you to plot both in the negative and in the positive, bearing in mind that G is a vector, right? So it can be positive, it can be negative. So, it's still the same. Either something like that or something like that. It's still the same, right? So that's essentially it. We're going to solve a couple of questions. Another one is this one, which says sketch the variation of free fall. And they've given you the graduations already. So we're going to solve those questions together so that we can be able to understand it. But essentially, the above statement is true. The gravitational field strength is a vector, and this means direction matters when we talk about this quantity. When we're plotting the graph, it can also be negative because it's also a vector, depending on the direction that you're moving in. So consider the following example. If you are standing in between, so let's say this is you, and you're standing between the Earth and the Moon, you're going to experience forces from both sides. So they'll reach a certain point where the resultant value of g, the gm over r squared, will be 0 at a specific point. Because at that point, the value of g will be the same, but opposite in direction. So we have a g in that direction and a g in that direction. And they're going to be opposite, but equal in magnitude, so the resultant g will be 0. So because g is a vector, there's a specific point where the resultant value of g will be 0. And it's also important for you to understand how to sketch a graph for acceleration due to gravity. But overall, I hope this video was helpful and it opened your mind about a lot of assumptions that you were making when it came to acceleration due to gravity.